As a maintenance person, you'll be servicing and repairing many different types of valves in various locations around the plant. The material we'll cover in this unit will give you a basic idea of why certain valves are placed in particular locations and how they work. Valves are used to control the flow of a fluid or gas in a plant system. When a valve is open, the flow begins. When it's closed, the flow is stopped. Besides starting and stopping the flow of a fluid or gas, some valves are designed to regulate the flow through a system. They usually do this by being partially open, responding to and regulating flow. This is called throttling. Valves come in all sizes, but whether small or large, they are all built to withstand vast differences in flow, temperature, and pressure. But as you'll see, the insides of all types of valves are similar in design and function. All types of valves have basically the same parts, but the parts don't always look alike, and they can be attached to systems in different ways. Well, for these reasons, valves are classified into categories that fit their particular descriptions. The most common classification is by the shape or arrangement of the disc. Other ways to classify valves is by their function, the conditions under which they operate, such as temperature and pressure variations, and the way they attach to systems, such as by flanging, welding, or threading. Now, since disc arrangement or shape is the most common way to classify valves, let's take a brief look at some typical disc arrangement. This is a gate valve. It is used primarily for isolating or stopping a flow. The gate valve disc is usually wedge-shaped, and it fits between the seats to form a tight shutoff. Gate valves are made in a variety of sizes, designed to withstand high or low pressure, and are usually found in liquid systems instead of gas systems. They're always either fully open or fully closed. The globe valve, however, can be used for regulating of flow. It's often called a control valve. The shape of the disc and the arrangement of the seating areas distinguish a regular globe valve from a control valve. By its design, the globe valve provides a tight seal where heavy-duty throttling is required, such as in a high-pressure steam system. Throttling is reducing the flow without fully stopping the flow. Another type of valve used for isolation is the butterfly valve. Now here, the disc is attached to the stem inside here, and it swings open or closed. Butterfly valves are light in construction and are generally used on large installations where pressure is not high, such as a circulating water system. In a diaphragm valve, the disc is made of flexible material, such as rubber or plastic, to provide a seal that prevents leakage into other working parts of the valve. These valves are most often found in systems with a flow of chemical fluids or harmful gases, where any leakage could be potentially dangerous. Finally, we'll look at a check valve. Now, these valves are used to allow the flow to go in one direction. Now, these are just a few of the most common valve types. Now, just remember that we haven't covered all of them here. What we're going to talk about now are the basic parts and function of several common types of valves that you're sure to see around the plant. Now, these are the basic valve components you should be familiar with. Always keep in mind that the shape and arrangement will vary with the type of valve you're looking at. Now, let's start down here at the bottom of the valve with the body. The body is the largest part of the valve. It provides the means to attach the valve to the component or piping system. Valves are installed in several ways. When they're to be welded in, the inlet and outlet stubs of the valve body are smooth and ready for welding or brazing. Now, brazing is similar to welding. The valve can be brazed using a standard brazing rod. The flange is another common type of connection. In this case, the valve is bolted in place, and the inlet and outlet stubs of the valve are flanged like this to allow for bolting with system piping flanges. A common method of attaching a valve to a low-pressure system is by threading. Threaded inlet and outlet stubs look like this. These are the ways a valve can be connected to system components. A valve can also be designed to change the direction of flow within a system. Now this is a globe valve, and we can see that the direction of fluid flow goes through this valve body in more or less a straight line. In an angled globe valve, the direction of the flow is caused by the change in the shape of the valve body. Inside the valve body is the seating area. The seat is a stationary part of the valve. It is here that the disc closes on the valve body. The areas where the disc and seat come in contact must be smooth and fit perfectly to completely stop the flow of fluid or gas through the valve. The seat is often threaded or welded into the body of the valve. In high temperature, high pressure systems, a combination of threading and welding is used to prevent leakage between the valve body and seat. Here is a threaded seat and a welded seat. Obviously, the threaded seat is easier to replace should damage occur to the seating area of the valve. Sometimes a combination of these is used. The seat is threaded in and then welded. On some valves, the seat is cast as part of the valve body. The materials used in constructing a seat will vary depending on where the valve will be installed. For low pressure, low temperature systems such as service water, the valve seat may be made of bronze or a Teflon type material. In systems requiring high temperatures and pressures, the seating area must be very strong. Stellite, a commercial name for an extremely hard metal, is often used. This metal has proven to be highly resistant to damage due to leakage of steam. The disc is part of the valve that presses against the seat to stop flow. Now, when a disc is partially open, that is, not completely closed against the seat nor fully raised, it is in a throttled position. This partially open or throttled position is used to regulate flow. Now, many discs like this one are attached to the stem that connects to the valve hand wheel or operator. The stem transmits the rotation of the hand wheel to the disc inside the valve. There are several ways to attach the disc to the stem of a valve. One way is called the slip type joint. The disc slips over the end of the stem, and the valve body will prevent the disc from slipping off the stem. Another method of attaching the disc to the stem is threading. The disc is threaded onto the stem like this. Some discs and stems found on inexpensive low-pressure, low-temperature valves are manufactured as one piece and cannot be disconnected. The bonnet provides structural support for the remainder of the valve internal parts. The shape of the bonnet is determined by the type and shape of the disc, because it provides housing for the disc when it is not closed on the seat. The bonnet is attached to the valve body by bolting, threading, or welding. This recessed area is where the stem comes through the bonnet. It is called the stuffing box. There's packing inside the stuffing box to prevent leakage through the bonnet, and at the same time to allow the stem to rotate. The packing is made of a material that can be compressed to form a seal around the stem, but still allow for rotation. To hold packing in place, a packing gland is attached. The packing gland is also used to adjust the compression of the packing, which in turn will control leakage through the stem and bonnet. There are several types of packing glands. This one is a solid piece that can be bolted to the bonnet. Another type like this is threaded to the bonnet. The hand wheel controls the movement of the disc inside the valve. It can be turned manually, thus the name hand wheel, or it can be operated by an electric, pneumatic, or hydraulic motor. Let's take an even closer look at some of these valves for a moment. You see here bridge wall markings. They provide very useful information. They indicate how the internal parts of the valve are arranged. By knowing how the parts are arranged inside, you'll be able to tell how the disc closes on the seat of the valve. Bridge wall markings on this valve show that flow comes in from the left, and then passes through the open area of the seat to come through this outlet. An arrow or set of letters also may be used to show the direction of flow through the valve. You'll find service markings on the valve too. These will indicate the operating range of the valve. For example, on this valve, the number 200 is the maximum allowable pressure that can safely be placed on the valve. These letters, WOG, stand for cold water, W, oil, O, and gas, G. They are for pressure ratings other than steam. Anytime you replace a valve in a system, you must be sure that the replacement valve meets the same specifications as the original valve. It must be installed to allow proper flow from the system through the valve and out again. Normally, a valve is installed so that the high pressure from the fluid or gas is under the disc when the valve is closed. In that way, there will be no pressure on the valve packing, and this reduces the danger of leakage at the place where the stem goes through the bonnet. If the valve were installed incorrectly, the other way around, there would be pressure on the packing when the valve is closed. In this case, there could be leakage that would require more maintenance. Careful installation is very important for the proper operation of the valve. The bridge wall markings will help you make the correct installation as well as tell you the arrangement of the parts inside the valve. Well, next we'll look at some of the different types of valves and how each is used in plant systems. First, though, we'll take a short break. This is a gate valve. You see a variety of gate valves around the plant. They're all fairly simple in design and function when compared to other valves that are built to regulate a system flow. Gate valves are placed where straight free flow is desired. Now, free flow simply means that when the valve is fully open, there's little, if any, interference with the rate of flow through it. You can see here that the disc of this gate valve lifts completely out of the line of flow. Externally, the gate valve looks quite like another valve we'll talk more about later, the globe valve. But the internal parts are different. Gate valves have two vertical seating surfaces. This cutaway shows the two vertical seating surfaces of a typical gate valve. Now, gate valve discs, which are sometimes called gates, are made in two ways: a wedge shape, which you see here, and a double disc. The wedge-shaped disc fits between the seats and forms a tight shutoff. It is directed by a set of guides that keep the disc in line as it closes. The disc does not touch the seating surface until the closing point is almost reached, and then the disc is wedged in between both seats. The wedge disc may be split down the center. In this way, each half will rest somewhat independently on the opposite valve seats. The double disc type is made of two separate discs with a spring mechanism between the discs. The spring holds each disc in place against its seat while the valve is being operated. When the double disc is lowered, there is no wedging or jamming action as it closes over the seat. This feature makes the double type disc particularly adaptable to motor operating mechanisms, such as steam stop valves. Instead of wedging action, the double disc is seated by system pressure. Pressure from the high pressure side causes the disc on the low pressure side to seat tightly. This means that it can be used for high temperature applications. The double disc will not jam as its metal expands under an increasing temperature condition. The seats on a gate valve are either fixed, built into the body, or are replaceable like these. Small gate valves are usually made with fixed seats, while large ones most often are equipped with replaceable seats. This is a practical consideration. Small valves are not usually welded into a system, but large valves are. So if the seat on a large valve is replaceable, the valve itself can stay in place and the damaged seats are replaced. Gate valve stems also come in two varieties, rising and non-rising. Some rising stems are threaded through the hand wheel so that when the hand wheel is rotated, the stem rises through it like this, while pulling the disc up. Other rising stems are bolted or keyed to the hand wheel and threaded through the stem bushing. Another common type of stem that you'll find on gate valves is the non-rising stem. Now, this is especially useful where space is limited. On these valves, the stem is bolted or keyed to the hand wheel so they rotate together. The disc is threaded to the stem and threads itself up the stem as the hand wheel is rotated. Notice that there are no threads here on the stem. Now, this keeps the stem from rising when the hand wheel is rotated. The non-rising stem valve is well suited for mechanical operation since the stem will not get in the way of an electric or hydraulic motor. Now, the rising stem valve does have one advantage. The amount of stem protruding from the hand wheel indicates the position of the disc. Now, you can tell at a glance whether the valve is open or closed. On the non-rising stem valve, an indicator should be attached to show the position of the valve. Usually, it's a simple arrow like this. Both types of gate valves may be equipped with a limit switch. The limit switch can be hooked up to light panels that show the position of the valve, so it can be observed by operators in other parts of the plant. Gate valves are made of various types of material depending on where they were used. For example, valves that are attached to low pressure, low temperature systems are normally made of bronze or brass. Cast iron valves are often found on low pressure steam systems or for lubricating systems. Valves used in high pressure, high temperature systems are made of special alloy metals. Stainless steel is used where there is a possibility of corrosion to the valve. You'll find a list of metals and valve applications in your text. Take a look at it. After a short break, we'll talk about some valves that are designed for throttling and flow regulation. These are some of the types of valves we're going to talk about now. Unlike the basic gate valve, which is used mainly for on or off service, these valves are used to regulate the system flow. Some of them are used in liquid or gas systems, while others have very specialized functions. We're going to start with this one, a globe valve. The design of a globe valve gives it much more flow resistance than the gate valve we've talked about earlier. This globe valve has a horizontal seating surface, which causes a large pressure drop across the valve. As fluid flows through the valve, a pressure drop occurs. The outlet pressure is lower than the inlet pressure. Another body type is the angled globe valve. This design helps to eliminate the need for adding elbows to change the direction of flow, thus reducing the number of joints. The fewer number of joints, the fewer points leakage can accrue. Now, both of these surfaces are built to provide a tighter seal for positive seating than is found on a typical gate valve. The shape and arrangement of the disc on a globe valve is varied depending on the type of service it's designed for. For example, this is a globe-type disc. It seats against a tapered, flat-surfaced seat. Valves with this arrangement are normally used in low-pressure, low-temperature systems. Another type of disc you'll see on globe valves is the composition disc. The composition disc is often made of material other than metal, such as Teflon. Often the seating surface is formed by a rubber O-ring like this one. The plug-type disc has a wide seating surface. Now, this kind of globe valve enables excellent throttling characteristics for flow control. It can be used under all pressure and temperature conditions. This needle valve is a variation of a globe valve with a plug disc. Now, the plug goes well down into the opening formed by the seat. This gives the valve extremely good throttling ability. Many globe valves are made with a seating area above the disc, like this one. It's called a back seat. When the valve is fully open, the disc will seat against the top of the bonnet. This keeps system pressure off the packing. Manufacturers advertise that packing adjustments or repairs can be made while the system is pressurized with the valve on its back seat. However, for personnel safety, we recommend that you do not perform valve maintenance while it is under pressure, even if on the back seat. Globe valves are usually made with a rising stem, similar to the rising stem of the gate valve. The stem is threaded into the bonnet or yoke bushing. Like gate valves, the specific function of a globe valve determines the material used to build it. You find more information on the types of globe valves and how they're made in your text. The preceding types of valves are good for high pressure and high temperature. The following valves are used for low pressure, low temperature application. Now we're going to look at two valves that are very much alike, a plug valve and a ball valve. And in contrast to most other types of valve, they do not have discs which raise and lower. The plugs on these valves, or the ball in this case, open by rotation. And when the valve is actuated, the ball makes a 1/4 turn, starting and stopping the flow very quickly. Usually this design does not provide the same tight sealing quality of the globe valve, but these valves aren't generally used in systems requiring a tight shutoff. Often you'll see plug and ball valves on lubricating systems, such as on a duplex strainer. A plug or ball valve can be single port, or it can be multi-port valve. Here is a three-way, three-port plug valve. There are three different flow paths available for the flow of a fluid. But if the valve is not lined up to allow full flow, a throttling action will take place. It's not good to let that happen, though, because the fluid will put pressure on the seals around the disc as it is throttled. The seals can be damaged by this pressure, and repair work would be needed. The seats on the plug valve are usually built into the body. Many plug valves are equipped with plastic-coated self-lubricating seats. The others must be manually lubricated. This one works just like a cup lubricator for a bearing. To do this, a lubricant screw attached to the top or bottom of the valve is rotated and lubricant is forced into grooves. The lubricant enters the grooves at a higher pressure than the system pressure. This keeps any solid particles in the system flow from getting lodged between the disc and valve body. The plug valve is very adaptable to systems carrying slurry. Slurry is a fluid often containing large particles. Often the valve will indicate which way the flow is going. For instance, on duplex strainers, the handle will point to the strainer with the flow through it. In a regular on-off ball or plug valve, the handle is usually in line with the post. So if the handle is lined up with the pipe, there will be flow through it. This is a butterfly valve. Now, these valves are normally found in low-pressure, low-temperature systems. Butterfly valves are useful on large volume systems where space is limited. The disc on a butterfly valve is the same diameter as the piping it is attached to. When activated, the disc turns 90 degrees from the fully closed to the fully opened position. The position of the butterfly valve can easily be observed. When it's in line with the piping, it is open. When it is perpendicular or across the piping, the valve is closed. A resilient natural gum rubber is used for the seat of most butterfly valves. This provides a firm fit and tight seal when the disc closes on the seat. The gum rubber seat can't easily be nicked, and it'll fit into any small indentations on the seating surface of the disc. Another type of valve with seating surfaces made of flexible material is the diaphragm valve. Now, the disc on a diaphragm valve is made of rubber, neoprene, or soft plastic. This type of valve provides very good control and sealing qualities in systems that carry abrasive or corrosive fluids. Although somewhat different in design, the hand wheel on a diaphragm valve is like those found on a gate or globe valve, and the bonnet is similar to the bonnet on a gate valve. It is large enough to provide a storage area for the compressor when the valve is fully open. On a diaphragm valve, a compressor is connected to the stem, And when the compressor is lowered, it presses against the diaphragm. The diaphragm itself is flexible, and when pressed against the seating surface of the valve, it will stop flow. It gives an excellent seal, even when slurry is carried through the valve. Now, this is a piece of diaphragm replacement material. You can see how soft and flexible it is. Different grades of flexible material are used for these valves, depending on the type of service they will give. Unlike the other valves that we've talked about, the diaphragm valve has no packing. Packing is not necessary because the diaphragm forms a boundary against penetration of fluid pressure on the stem and the bonnet union. There are two basic body designs used for diaphragm valves, the weir and the straight through. As the name implies, the straight through body has no obstructions where the diaphragm seats. The bore of the valve is the same as that of the piping it's attached to. The weir, on the other hand, has a raised surface where the diaphragm seats on the valve body. This allows for the use of stiffer diaphragm material, but reduces the area of flow through the valve. You'll find additional information about material used in the manufacture of diaphragm valves in your text. There's one more basic valve design I'd like to talk about before we break. It's the check valve. Now, a check valve will permit flow in one direction only. It is designed to prevent any backflow of fluid within the piping. However, most check valves cannot be used as stop valves. Most will only close if the flow stops or if for some reason tries to reverse its direction. There are three basic types of check valves: the swing, the lift, and the stop check. On the swing check valve, the disc is attached to a pivoting arm or hinge pin. Flow through the system keeps the arm raised and the disc up. If flow is stopped or reversed, the disc will shut. A cap on the valve body gives access to the disc for maintenance. The disc on a lift check valve is not pivoted by an arm. It is lifted when system pressure is greater than the weight of the disc. This permits flow through the valve. Guides attached to the disc keep them in position and prevent the disc from cocking or jamming against the seat. Lift check valves are well suited for service in systems with a fluctuating flow, such as steam, air, gases. The slamming does not affect them as it does the swing checks. The third type of check valve, the stop check, is like a modified globe valve. When the stem is completely down, the valve is closed, but when the stem is raised, the disc operates like the disc on a lift check valve. It responds to system pressure. As system pressure increases to overcome the weight of the disc, it is lifted and flow can be carried through the valve. This type of valve is common to the boiler feed isolation valve. Well, we've covered a lot of ground in this segment of our unit on basic valve design. Be sure to review your text so that you understand the differences and similarities among the valves we've seen. Well, after a short break, we'll talk about how these valves actually operate to regulate flow through the systems of your plant. In the last segment, we talked about the basic design of several types of valves you'll be working on in the plant. We saw that disc shape and arrangement is often what determines how a valve will be used. But regardless of how they're used, the internal parts of each type of valve are similar. With the exception of the check valve, they are all operated externally by a hand wheel or a power operator. Now we'll find out how some of these hand wheels and mechanical operators work to make the valves open and close and regulate flow. The most common type of operator is the hand wheel. This valve has a modified hand wheel called a knocker. It's a type of hand wheel that is usually found on very large hand-operated valves, which are designed for heavy-duty service. The hand wheel on the knocker valve is weighted and has approximately a 1/4 turn play. The valve is opened or closed in this way. First, the hand wheel is turned in the opposite direction of the desired rotation. Then it is turned as hard as possible in the desired direction, slamming the stem into motion to raise or lower the disc. Hand wheels can be equipped with other types of adapters to make them easier to operate. Sometimes a chain running through a pulley is attached, or an extension arm might be put on the hand wheel of a valve that's hard to reach. Motor-driven operators are often used in place of the hand wheel. Electric, hydraulic, or pneumatic motors provide ease in handling, and they allow remote control operation. Electric solenoids are usually used for remote operation on short stroke applications, usually a quarter of a turn or less. Electric motors are connected to the valve stem. They're usually run at low speed, but are high powered. When the motor is energized, the stem starts to rotate. A limit switch stops the motor when the valve is fully open or closed. Pneumatic and hydraulic motors operate in about the same way. The stem is rotated by a set of pistons that are activated by air or hydraulic oil. In this way, the stem is moved to open or close the valve. There are, however, some variations of the pneumatic and hydraulic operators. For example, they may be applied to a single piston, giving an in and out motion, or to a piston connected to rack and pinion, giving rotation. If pressure is applied under the piston, the disc moves up, opening the valve. The top side of the piston is vented, allowing the piston and valve to make a complete stroke. The reverse takes place to shut the valve. Electric solenoid valves are usually used to control the flow of air to the valve. They are either fully opened or closed and are not used for throttling. The diaphragm operator is run by air or hydraulic oil pressure. Varying the applied air pressure of the system causes the diaphragm to move. The diaphragm is attached to the stem, and as it moves, the stem also is moved and the valve opens. Well, so far we've talked about the common types of valves you'll find used for industrial purposes. Just now we've seen how hand wheels and mechanical operators work to make valves open and close and regulate flow. After a short break, we're going to look at some variations on these common valves and how they're designed to operate for specialized purposes. In the meantime, look over your text and review what we've covered so far. Besides the valves that we've talked about so far that are all common to industrial use, there's a wide variety of valves designed for special applications. These not-so-common valves are used for specific purposes. They'll be found where corrosive or caustic chemicals are used, where cleanliness is very important or precise flow control is necessary. We'll get a feel for the wide range of valve applications and some of the difficulties that are encountered in operating valves under extreme conditions. Earlier, we talked about the operation and maintenance of a diaphragm valve. Well, let's look at two specialized variations of this type of valve, the pinch and the boot valve. Now, this is a pinch valve. It has a flexible tube which goes through the valve body and forms flange gaskets between the valve and the connecting pipes. The flexible tube is made of the material which has abrasion-resistant properties. Now, this enables the valve to handle and control a flow containing slurries, chemicals, processed food, or pharmaceutical materials. The flexible tube serves as a protective barrier or sleeve to form a seal, preventing dirt or other contaminants from entering or leaving the system. A disc or compressor arrangement is used to shut the valve, quickly pinching off the flow. System pressure and flow then force the sleeve open as the stem and compressor are rotated to the open position as well. Now, the pinch valve can be operated manually or with a power operator. The pinch valve has good throttling characteristics due to the smooth, straight flow path through it. Now, in contrast, on a standard valve, the path of flow is changed as it passes through the valve body. This causes a pressure drop to occur. However, the flow passes straight through the pinch valve, causing little or no pressure drop. Now, the boot valve is another variation of the basic diaphragm valve, and it is similar to the pinch valve. Like the pinch valve, the boot valve has a smooth, flexible tube running through it. There are two compressors that flex the boot to start, stop, and provide throttling action. The boot valve also has good throttling characteristics and is used for the same basic purposes as the pinch valve. With a double compressor, the valve can be shut quickly to stop flow, with each side of the boot flexing to close the valve. Wear on each is reduced by half. That gives the valve added life. The next valve I'd like to talk about is designed for cryogenics. Now, cryogenics is the term used for the storage and handling of substances at very low temperatures, such as liquid nitrogen or oxygen. Now, this poses special problems for the design characteristics of the cryogenic valve because liquefied gases are extremely cold and will cause most valve materials and parts to become brittle. Well, heat gain is another problem associated with the use of valves in liquid gas systems. This is because there's such a great temperature difference between the lines carrying and storing liquid gas and the surrounding atmosphere of the plant. Heat gain can be expensive because of the additional work that must be done by the cooling system to remove the heat gained. Well, even with very good insulation, there are always certain portions of a system that are exposed. And this is especially true of areas around valves. Thus, an effective cryogenic valve must be made to withstand extremely cold temperatures with a minimum of heat gain from the surrounding atmosphere. Now, when you look at a cryogenic valve, the disc and seating arrangement looks quite like a normal globe valve, but there is a difference in the stem and packing arrangement. The stem extends through a long, hollow operating tube to connect the disc to the operator. Around the outside of the hollow tube is a vacuum jacket, which acts as an insulator. Thermal foam is placed at the top of the hollow tube shaft to provide insulation. The valve is packed at the top, or warm end of the valve, with chevron packing, or an O-ring, to ensure that there is no leakage by the valve stem. Gases in the liquid state are very expensive to maintain and store. Leakage must be prevented for another equally important reason. Certain gases, such as hydrogen, are highly explosive and could create great hazards if leaked from their enclosures. Well, cryogenic valves are usually constructed from materials such as bronze and austenitic stainless steel. These materials do not generally become brittle. Carbon steel found in many regular valves is not used for cryogenic valves because at very low temperatures it becomes as brittle as glass. Well, this is a common ball valve, a type of basic valve we talked about earlier. A special variation of it is the V-ball valve. The V-ball valve is finding wider use because, like the pinch valve, it has very low pressure drop characteristics and does not slow down flow through it. It also is resistant to clogging, which makes it adaptable to a wide variety of flow materials. For example, slurries such as pulp, coal, or ash can be controlled through the V-ball valve. Control is applied by a wedge shearing action. As the ball is rotated to close, any material that might clog the passage is sheared off. When a single disc valve is put into operation, all pressure drop across the valve is exerted on the area of the valve seat. Now, this force of pressure must be overcome by the valve operator. On high pressure systems, this means that the valve actuator must be very large to overcome the force of system pressure. And because of this problem, certain valves are designed with a double disc arrangement. Now, they're especially serviceable where system pressure is very high or where constant adjustments must be made to control the flow through a valve. This is a piston balance valve. The double disc arrangement on this valve allows the force exerted across the seating area to be as equal as possible while being directed in opposite directions. As we look at the double disc arrangement, we see that flow comes in from the left. In the closed position, the fluid pressure would press against the bottom of the top disc and against the top of the bottom disc, equalizing flow pressure. Even when the valve is open, there is still an equalizing force, giving the valve smooth operation. The double disc design can be varied to change flow characteristics through the valve or to change the operation of the valve, such as decreasing the response time of the valve's action. Well, let's compare the regular disc with the double disc valve designed for special flow requirements. The general flow characteristic curve for single disc valves looks like this. We are plotting flow versus valve opening. On the graph, the valve position is plotted with the horizontal axis, and we'll plot the percent of flow along the vertical axis. When the valve is fully closed, there is, of course, zero flow. As the valve is opened, flow begins through it and continues to increase until the disc is in the fully open position. Now, this method of flow control is suitable for many applications. However, when fine flow control is required, such as during controlled chemical addition or for boiler feed flow, we need to have precise flow as the valve moves. A method used for this type of control is a valve designed to have linear flow characteristics. An example of this type of valve is one with a double disc. Now, here are the characteristics of linear flow through a double disc valve. As before, we will be comparing valve opening versus percent flow. Along the horizontal axis, we'll plot the valve position. Then, along the vertical axis, we'll plot the percent of full flow. For flow to be linear, the characteristic curve must be a straight line forming a 45-degree angle with the axis like this. The graph shows that for each percent the valve is opened or closed, the flow will change by the same percent. If the valve position is changed from 1/8 of the way open to 1/4 of the way open, flow will increase the same amount, by 1/8 or by 1/4. Now, this is linear flow. Linear flow characteristics are often required when flow through the valve must be carefully controlled. Well, we've seen some interesting variations on basic kinds of valves, and we've talked about the types of industrial uses they're designed for. We also took a brief look at how flow through a valve varies with disc design and what can be done to change the flow characteristics of a valve. Be sure to go over this material in your text and review the chapters on basic valves as well. Good luck.